Hello everyone, this is Dr. Ruby, and this is the first of the lectures for Module 5, the types of muscle contractions. I'm sure that you'll find the topics of this chapter quite simple and maybe things that you've heard of before. However, I feel better going over all of this before we get into the more complicated types of contractions. Please again read these objectives on the next two slides. Make sure that you look up any terms that you're unfamiliar with. And you can use that Evolve website to find those definitions of the key terms. That's probably the easiest place for you to do that. Here are some more objectives. And again, one more slide of objectives to know for this chapter. There are three types of muscle contractions: concentric, eccentric, and isometric. A concentric contraction is the type of contraction wherein a muscle contracts and shortens. The muscle generates the force that moves a body part to create the joint action that is occurring. It is therefore termed the mover. If the force of the muscle's contraction is less than the resistance to the muscle's contraction, the muscle will lengthen instead of shorten as it contracts. This is called an eccentric contraction. An isometric contraction is one wherein the muscle contracts and stays the same length. The force of the muscle's contraction is exactly equal to the resistance force. Concentric contraction of the brachialis muscle is shown on this slide on the left. The arm is fixed and the forearm is mobile. The arrow within the brachialis shows the line of pull of the muscle. The red curved arrow represents the strength and direction of pull of the brachialis acting upon the forearm. The straight brown arrow represents the strength and direction of pull of gravity acting on the forearm. In the eccentric contraction scenario on the right, the force of the contraction of the brachialis is less than the resistance force of the weight of the forearm. Therefore, the forearm extends with gravity, causing the brachialis to lengthen. In this scenario, the force of the contraction of the brachialis is exactly equal to the resistance force of the weight of the forearm. The brachialis therefore does not succeed in shortening and flexing the forearm, nor does gravity succeed in lengthening the brachialis and extending the forearm. This illustrates isometric contraction of the brachialis. During isometric contraction, no joint action takes place, and therefore no mover or antagonist exists. Resistance exercises add to the force of resistance that the contracting muscle must work against. Figure A on this slide demonstrates an example of resistance exercise by adding resistance to flexion of the forearm at the elbow by placing a weight in the person's hand. Figure B shows added resistance by using rubber tubing that must be stretched for the person to be able to flex the forearm at the elbow joint. One example of concentric contraction is shown here with the person abducting the right arm at the shoulder joint against the force of gravity. This force of abduction is created by concentric contraction of the abductor musculature. As the musculature shortens, the arm is lifted up into the air into the frontal plane. The same person is now adducting the arm at the shoulder joint. Gravity is the mover force that creates adduction in this case, but the abductor muscle is eccentrically contracting to slow down the force of gravity. It is necessary to slow down the force of gravity in this type of movement to prevent the arm, forearm, and hand from slamming into the side of the body. In this illustration, the person is statically holding the arm in a position of abduction. In this case, the abductor musculature is isometrically contracting, equaling the force of gravity so that no motion occurs. A muscle does not change in length during an isometric contraction. A muscle is an organ composed of thousands of muscle fibers that attaches from one bone to another via its tendons, thereby crossing the joint that is located between the two bones. The central nervous system sends a signal through the neurons to every sarcomere of every myofibril of the muscle fiber to cause a muscle contraction. The sliding filament mechanism explains how actin and myosin filaments slide along each other. When cross bridges form and create a pulling force toward the center of the sarcomeres, the muscle is defined as contracting. If the bending force of the myosin cross bridges is successful in pulling the actin filaments toward the center, the Z lines are drawn toward the center of the sarcomere and the sarcomere shortens. The message for contraction is given to every muscle fiber of a motor unit, so every muscle fiber of that motor unit will shorten. In this result, a concentric contraction will occur. The myosin cross bridges will not be successful in bending and pulling the actin filaments toward the center if the force of resistance to the muscle shortening is greater than the force of the muscle contraction. The resistance force will actually pull the actin filaments away from the center of the sarcomere, and each sarcomere will actually lengthen. This would result in an eccentric contraction. If the muscle can equal the strength of the resistance force, the myosin filaments do not succeed in shortening the sarcomere, nor do they get pulled apart and have to reattach farther from the center of the sarcomere. Instead, they stay at the same binding site locations. This is an example of an isometric contraction, where the muscle remains the same length and the body parts do not move. On the next couple slides, you will see the objectives for Lesson 12-2. The brachialis on this slide is concentrically contracting. The motion that is occurring is flexion of the forearm at the elbow joint. The motion is vertically upward against gravity. Gravity is a force that pulls downward caused by the mutual contraction between the earth and our bodies. The force that gravity exerts on the mass of an object is then defined as the weight of that object. This illustration shows the scapula retracting at the scapulocostal joint. This motion is horizontal and gravity neutral. Therefore, the muscles of scapular retraction must contract as movers to create this motion. The trapezius, and especially the medial trapezius, is seen contracting in this figure. However, any scapular retractor might concentrically contract to create this motion. Figure C here shows the arm adducting at the shoulder joint. This is a downward motion. Does any muscle need to concentrically contract to create this motion? No. There are no muscles that need to concentrically contract to create this motion. The arm can be adducted with the use of gravity. Figure D shows the arm adducting against the resistance of rubber tubing. Even though this motion is downward and aided by gravity, because of the resistance of the tubing, shoulder adductors must concentrically contract to overcome the resistance and adduct the arm. Comparing the motor of a car to a concentrically contracting muscle is a helpful analogy to use when learning why and when concentric contractions occur. Figure A shows a car moving uphill or vertically upward against gravity. Figure B shows the car moving on level ground, or gravity neutral. Figure C illustrates the car moving downhill faster than coasting with gravity, or vertically downward and faster than gravity would create. During an eccentric contraction, instead of the myosin heads bending toward the center of the sarcomere, they are overpowered by the resistance force to contraction, and they are bent in the other direction. As a result, the actin filaments slide away from the center and the sarcomere lengthens. An eccentric contraction is defined as lengthening contraction. A muscle contracts and lengthens. When a muscle lengthens, its attachments are moving away from each other. This is usually not caused by muscle contractions in our body, but by an external force. In this illustration, if a person lowering a glass of water, the flexor muscles of the forearm at the elbow joint must contract to oppose the elbow joint extension force that is being caused by gravity. Without control of the muscular system, the glass would come crashing down to the table and break. Figure A shows a person who has just hit a ping pong ball with a forehand strike. The person is horizontally flexing the arm at the shoulder joint. To slow down the motion of the arm and to prevent it from moving too far, the person must eccentrically contract the muscles that do the opposite action of the forehand strike, i.e. horizontal extension. In illustration B, the girl has just thrown a ball up into the air by flexing the arm at the shoulder joint. This motion was initiated by muscular contraction. In this scenario, upward motion of flexion of the arm aids in throwing the ball up into the air. Eccentric contractions of the muscles on the other side of the joint, the antagonistic shoulder joint extensors, act to slow the upward motion. Comparing the brakes of a car to an eccentrically contracting muscle is a helpful analogy to use when learning why and when eccentric contractions occur. Figure A shows the car moving downhill, vertically downward, and slowing down by pressing on the brakes. Figure B shows the car moving on level ground and slowing down by pressing on the brakes. Figure C shows the car moving uphill, vertically upward, and slowing down by pressing on the brakes, slowing more quickly than it would have due to gravity alone. An isometric contraction is a contraction in which the muscle stays the same length. In this case, gravity is pulling the arm downward toward extension, and this man is holding his shoulder joint musculature isometrically to contract with enough force to equal the force of gravity. Isometric contractions can not only hold a body part up against the force of gravity, but can also hold a body part in position against any force other than gravity. This other force could come from another muscle contracting within the body or from an external force. When a person arm wrestles and the force of the person's isometric contraction is exactly equal to the opposing force from the other individual, neither force is capable of moving the body part, so the parts remain statically still. A muscle can create a force that can cause or modify movement of a body part at a joint. It can also create a force that can entirely stop movement of a body part at a joint. A muscle that contracts to create a force that holds a body part in a static position is said to fix or stabilize that body part. That concludes Part 1 of Module 5.